Good afternoon, everyone. Thank you, Andy, for the introduction. Let me start by introducing my co-authors. Dr. Ali Abu Ubaida, he's a research associate, and Dr. Chekuk now, also a research associate. We also have the support of the New Jersey Turnpike, but Frank Corso was the engineer in charge. So this project, I would like to summarize the process by which we implemented this fiber in bridge decks. The first one, we have an on-call agreement with the New Jersey Turnpike for the last 10 years. And part of that process is to develop their technical specifications. So we started with high-performance concrete, and over time, every year, we try to update the specification based on in-situ experience and the process, and then we come back and we do more work. And then we'll talk about how did we come up with the field implementation and the final conclusion. So this is the basis for what we did in almost 20 years ago. We introduced high-performance concrete to the state, and New Jersey DOT and the New Jersey Turnpike, between the two of them, they have about 6,500 bridges, and they needed the average age of these bridges is about 50 years, which they exceeded their design life. So they ended up changing or replacing a lot of their bridge decks. So they have a lot of what they call reconstruction by removing the bridge decks and placing high-performance concrete at the time. So for this, we developed a specification, and we added, unlike other states, we added the shrinkage limit to that by using the free shrinkage, but it was based on a study that we did for restrained shrinkage conditions, and we also included the blended aggregate as part of the mixed design itself. And part of the process that we have followed, even for high-performance concrete, is to do the laboratory work, then invite about 3 concrete producers and the plant conditions, try to reproduce those mixes, get the experience, and then try to do a demo in the field under field conditions by either pouring it from a chute of the truck or from a pumping. So the mix was designed for all these processes, and that's why it had to be very practical. So we developed many mixes, but the majority of them, they had some shortcomings, excuse me, when it came to implement them in the field. So we worked together with the concrete producers and with the contractors who are on call, or they have a contracted project with the Turnpike. They try to develop that kind of process. So this was a very useful process. It gave feedback to the agency what needs to be done. So in that process, we also realized that no matter what good of a concrete you have, if you have extremely heavy loads, that can be a problem, and especially during the construction phase. Sometimes we realize that the contractor would use water tanks, a truck which is very heavy, to pour the water in different barrels for the burlap to keep it wet. Sometimes with the concrete itself, when it's delivered, it's very tight. They end up going into locations where it affects the load path, and the fresh concrete might be under stress beyond what it's designed for. So some of the cracking really happened at early age, and for reasons that have nothing to do with the mix itself. So the mix as a material was optimized for a lot of the factors. So there are other things that we needed to do, and that led us to design mixes we call it high airless strength for the first 6 to 8 hours. We ended up using different types of rebars. We used, for example, which we also experimented with a project for using the MMFX steel. This is one of the best performing rebars in the study that Turnpike did compared to all rebars that we have done. And the last part was, what if we use the fibers to be able to mitigate some of the cracking that we have no control of? For example, in the negative moment region, you will end up having cracking, and even in AASHTO, the design is silent about that. So we tried to figure out a way to control the shrinkage, but at the same time try to use stronger fibers to kind of intercept, if there's any cracking, to intercept the cracks and keep it at a small size. So some of the fibers that we have used steel fibers, which I think the producers or the contractors in general were totally not happy with that. It's very hard to work with it, so you need to have a special volume fraction to make it more workable. And we used also the synthetic fibers, polypropylene fibers, and the macrofibers and the microfibers. We use different length of fibers for these synthetic fibers. And we use different fibers from different producers, so in the specification when we write it, we don't want to bias that to one producers of the fiber. And during our kind of review of what has been done with other states, we found out that there are really very few states until now that are really applying, and there was about 7 states that have had specifications that directly related to pouring decks with fibers, synthetic fibers. So I think with our hope that with this study, which has been ongoing for almost 5 years now, that this will help other DOTs also, jump on the wagon and start the use of the fiber. So during our lab, we tried to also, we discovered that when we blend the aggregate, for example, this is before we started using the fibers, there was a very good performance in the mix, meaning that the shrinkage was reduced, better results for the rapid chloride permeability. So we ended up now requiring to have blended aggregate. And some of the concrete producers, they already blend their aggregate, so they already have compartments. So you can see this blended here, HPCB. So whatever has a B at the end, it would be a blended aggregate. We also tried to use the amount of fiber. Unlike what we do in the lab, you can put a lot of fibers, but then the workability will not be good. And we tried that. And we found out there is an optimum point on how much you can put on the fiber, how much is recommended by the manufacturer, but also how much would be a workable mix for finishing, for workability, for pumping. So we had to keep that in mind. So we ended up with these different mixes, and some of them, we had 5 pounds of fiber, 5 pounds per cubic yard of fibers, and some of them, and E is the type of fiber for Euclid, made by Euclid Chemical Company, and the S is from Sika fibers, and we had also the steel fibers there. So the blended aggregate, we saw that we got very good results out of mainly the compressive strength and the tensile strength. And the difference in that, the one with the fibers, you had a lot of ductility post-cracking. In other words, you got, maybe this is not very evident, for the concrete deck, but at least our hope was that the fibers will keep the crack width narrow, and thus we don't have the conditions without fibers. So the idea was, can we put maybe concrete decks made out of HPC, but also at the same location, try to put concrete decks made out of fiber reinforced HPC and do one-to-one comparison, because they're under the same loading conditions and same environmental conditions. So we could see that under restrained conditions, we also did use the restrained ring, and we monitored in the lab which mix had the best potential for minimizing the cracking density and the cracking area. We did that on all the mix, and we also the wet curing and the dry curing, meaning that without air dry. This is one of the conditions, because the contractors were complaining that 14 days of wet curing adds a little bit more cost to them. And then this is a typical mix that had fly ash, and all what we do to make it easier for the producer, they add 5 pounds to the truck, to the mixing truck, the transit mixer. So they batch it as if it's an HPC, and then they run the mixer for about the drum rotated at a certain speed for about 2 minutes, and then they keep it running at a lower speed when they're driving it to the site. So this was the way we wanted to do it, because it was fast production based on the requirement of the producer. And you can see this is the general specification. they require, the compressive strength at 28 days, at 3 days, flexure strength. We also recently, about maybe 4 years ago, we tried to replace the rapid chloride permeability. By now, they do what they call the services study. So we ended up putting this part of the study. And if you look at the quick results, there were only a few mixes that did not really satisfy the standard specs. You could see this V5 mix and this S5 mix. All the others, all the limits were within the. And if you look at what is the reduction in the cracking, this is based on the lab at this point. You can see all of the mixes have produced a reduction in the cracking by adding the fibers. And you can see that the maximum, we got about 83% reduction. And also, the free shrinkage was also reduced drastically because of that. So we were doing well on the shrinkage and well on the cracking. So once we selected one of the good candidate mixes, we talked to the contractor and we asked them to mobilize as if they are doing it for the deck. And we put some slabs right underneath the bridge. The bridge is elevated around, it's about 14 miles. If you go to New York area, this is the highway leading to the Holland Tunnel. So it's all elevated and very flexible, old structure built in the early 70s. So we did the study on those mixes produced by pumping or by, from the chute, from the truck directly. They did the finishing. The producer of the fiber the chemical was there, and they, for the broom finish, they were having some difficulty, so they had to clean the broom every time they do the finishing because the fibers get, in the way, and then the finish doesn't come out right. So when they did that with some training, they were able. And we did the same testing, same samples. We took them back to the lab. And once the demonstration, we solved all the technical logistics of pouring the concrete. So we selected about each span is a continuous 3-span, about 200, 225 feet. And we alternated the mixes with fiber reinforced high performance concrete and with the high performance concrete mixes. And it was very well pumped. This shows one of the lanes and the deck, the span. And then notice that there is traffic active on the other side lane. And this is a floor beam stringer system. So the floor beam movement affects how the stringers and the continuous span. So the concrete was under stress at early age. And then what we did is we asked to survey the cracking at different stages. So we wanted to confirm that what we're seeing in the lab, you can also see it in the field. So we did the first fingerprints of like before opening it to traffic. After the curing, they removed the curing. We did the mapping. We measured the crack width and the crack length. And we had an army of students do that. And we marked them, we colored them. And we did that more often. So the last one we did after almost a year, and this is when they decided that the bridge is ready to be open to traffic. Then we went back after another year. We asked them to see, because before they opened to traffic, they micro-milled the bridge about maybe 1/8 of an inch was micro-milled. This is a practice that they use. So we asked them to see if the cracking, because of the traffic, if the cracking are opening or closing. So you can see that what happened when they micro-mill. If you can imagine the crack, it's almost like a wedge. So when you micro-mill it, the width of the crack is going to be smaller in any way, for both, for HPC and for the FR-HPC. Using the fibers, we were getting continuously a reduction in the number of cracks and in the crack sizes. And we looked at also the cracking area, which is the length and the crack width. We added them up per square foot of the length. And so we looked at, and we looked at what happens to the crack sizes. So we did a kind of the statistics that we have. So you can see the red color is the distribution of the crack sizes and the deck for the FR-HPC, whereas the blue color is distribution of the crack sizes for the HPC. This is the last time we did the survey, and this is after it was opened. The graphic, you can see when they micromill it, the cracks for the FR-HPC were less than what is perceived to be a hairline crack, the 0.016 inches as ACI required. The HPC had almost, many cracks were below that too, but a lot of the cracks were more. So you can see the mean value here much higher with much more cracks above that. So that is shown that here there is a reduction in the cracking, and it is very beneficial to add the fiber, especially at that. Maybe if we put more fibers, we would have had much more, but that's from the practical point of view. So in summary, I think our field study, in addition to our lab study, shows that there is about almost 30%, this is the number that we were seeing in the lab, and in the field, we were able to say that there is about 30% reduction in the cracking, in the crack width, which means a lot in terms of the durability aspect. The minute you get the crack size to be lower than what's the limit, that would be an excellent performance. And the total number of cracks, the total cracking area is also reduced by about 30%. So I think now this is the fiber HPC is going to be a standard mix for the turnpike. Whenever they feel like there is a different loading condition, they will try to use fiber HPC. Thank you for your attention. I'd like to acknowledge all the sponsors of this research. Thank you very much.